I'm excited to finally be standing here after having attended. This is my 5th KVM forum in a row, and finally I can talk about what I've been doing all the time. So just to give a few words about myself, I grew up with the fathers of object-oriented programming and made my master thesis for Ole Johan Dahl, one of the fathers of Simula, and I kind of had a computer science background, but then after a while I ended up working on very exciting projects on RDMA back in the 1990s, and I took my PhD on an RDMA performance topic, and then I went ahead and worked for several companies before I went back to work on RDMA again. About the same time I started to attend KVM forum conferences. The team that I work for is located or kind of based out of Oslo. We have people in several in Norway. We have several people out throughout the organization in Oracle, but much of the root of the project is from an old Norwegian company called Norsk Data, which made mainframes back in the 80s, and we have then been, the people that work in this department have been hired from between several companies over the years, but some of them have kept the same office in the same building all the way along. And this company was, this startup was then acquired by Sun, and Sun was then acquired by Oracle, and that's how this group of people ended up working for Oracle. And I joined them after a while. So the agenda for today is a project. Our project, I'll talk a little bit about the target for our development, and I'll talk about our goals and why we ended up using virtualization and QEMU, and give you a little bit of taste, a kind of high-level taste of the tool set that we have been developing and some of the use cases. And I'll tell a little bit about what we achieved and what we could have achieved. So this is a picture of the device under test, or in fact the device that we didn't have back when I started on this project. The device existed only as a few lines of RTL in the hardware group. But this is what we now have available, and the topmost entries here are the PCI Express form factors of this card, and the bottom is the one that's integrated into the Spark, the new Spark CPUs. And it's a fairly complicated piece of hardware. It has a highly asynchronous model. It supports lots of fancy features like SRIOV, and it has integrated virtual switches. And it has fairly sophisticated MMU, which is compatible with the CPU page tables. And it also has a lot of hardware features for offloading Ethernet over IB and IP over IB. So, for those of you not familiar with InfiniBand, InfiniBand is kind of different from Ethernet in that the standard is kind of defined both by software and hardware. the host channel adapter, which is a InfiniBand standard term, equals a network adapter, but it defines only the set of operations to support. It doesn't tell if hardware or software is going to implement it. And the standard defines the rough semantics of the verbs, the requirements, but not the syntax and implementation. So that means that there are quite a lot of room for implementation differences and challenges in that area. So the Linux implementation is what many of you know as the RDMA, or Remote Direct Memory Access support. We used to, back in the old days, we used to call this a shared address space or remote address space, but RDMA is the modern term for it. It has a kernel and a user space part, and the kernel and user space interfaces are quite similar, but the reason why we have a user space part is because we want to be able to bypass the kernel for as much as possible. And the standard is quite a beast, more than 2,500 pages, but still there are details that are left to implementations. So this felt a bit like this guy here, which is a guy from a Norwegian adventure, old Norse adventure. The glittering thing there is the castle where the princesses have been captured by the trolls, and this guy is going to rescue, and nobody believes that he will ever make it. So what was challenging for me with this project was that we were able to get in fairly early, before hardware was even nailed. And we could kind of start. The software team was kind of left to itself in the beginning, so we were free to do whatever or shape the project in the way we thought useful. And so it was kind of an adventure, so that's why I think this is an illustration of it. And as you might know, good tools is often half the work when you have a big task. But to get good tools, you need to pay for it in some way. You could probably get this one at the garage sale for the left one at the garage sale for free almost, but you have to pay some more to get this right-hand side tool, but the quality will be much better. So we decided we need to do this. We had been out there and done projects like this before, so we knew we'd have to really invest in the tooling to be able to accomplish what we wanted to. So some of the survival rules we put up was that we wanted to set time aside to develop tools. And as you know, it's very easy to get the answer that, yes, that's a great idea, just do that, as long as it doesn't take any time. But we managed anyway to kind of, because the challenge is of course that if you need to write good tools, you will spend time with that tools, and in the meantime nothing happens on the real coding side if you don't have a lot of people, which we didn't. The other fundamental success criteria was that we decided we want to write the software as it was going to be released to start with. We didn't want to have a lot of if test environment and else something else. We wanted to be able to have the code start writing the real code from the beginning. And we did that also because we realized that we have to have a lot of tests. There's lots of dimensions that we need to cover to be able to deliver something on this. And we needed to have those tests not only working during the test, the early phase, but we wanted to be able to use the same tests also when we received the hardware. So that meant that APIs was very important for us. So we tried to define the APIs at various points in our test bed, so that we could reuse as much as possible of what we developed for different kind of scenarios as we move forward. And we also decided very early to do test-driven development, not test-driven to the extreme sense, but in the sense that whenever we have an issue that is serious enough, we write a test for it and deploy that test so that that will never happen again, that error. And that has been a great success. And we also early on deployed continuous integration with Jenkins, and we also added, after a while, Garrett, and we check all our commits through that. I'll come back to that, details on that. So our motivation for using virtualization, of course, to be able to start early, we didn't have any hardware. We needed to create a fake hardware environment, and we needed to, and I also needed, from my understanding as a software guy, I needed to get more insight into how PCI Express worked. Since the last time I worked on a driver, it was a PCI driver. So what was this PCI Express thing? I had a long way to go. So I spent a lot of time reading QEMU code and to understand what was going on, and of course the standards. But it's really useful to be able to have emulation to look at. Another challenge we had was that since we had been working with hardware, broken hardware before in our team, as a software team, we really wanted to avoid having to solve very difficult problems or work around very difficult hardware issues after tape out. So we really wanted to be able to get ahead of the hardware developers and find bugs before tape out. And we managed to do that, actually. And of course, as a software team, once hardware is out, once hardware is available, the software team is under pressure to get things done. So for our own hearts and survivals, we wanted to minimize our pain by being ahead of things. That part we didn't quite succeed in, but it improved. And the final point here is also very important. There's always limited hardware, so using virtualization we could do more with the same amount of hardware. Do more testing, get more out of the hardware we had. So why did we end up with QEMU KVM? Well, of course it needed to be open source or available source. Some people wanted me to use, some of the engineers in the project were already using VirtualBox. So, and since VirtualBox is owned by Oracle, that was obviously something that would have been interesting as well. But I had used QEMU in a previous project, so I really wanted to use QEMU. But I had to sell it. But then came the issue of PCI Express, and of course nobody else supports PCI Express emulation. Not even QEMU at that time. I had to pick the patch set for Q35. So then I got a good excuse for using QEMU. Of course, also wonderful copy on write support in QCOV2 has saved us a lot, because we had these expensive servers with very expensive disks, but the disks are very small. So we couldn't really afford to have, we needed to save disk space to be able to run as many virtual machines as we wanted. So that QCAV2 came very handy. We also had a number of other challenges. We wanted to have a flexible solution so that we could cover different types of simulations with the same system. And we had this RTL and the RTL developers, so we wanted to hook into the RTL development as soon as possible. So we were questioning ourselves, could we automate an interface to this RTL early on so that we could actually start finding bugs even before this hardware was available or was working to the full extent. Yeah, I already touched the hardware, the server part. Yes. Here is the picture, kind of abstract picture of our setup. So we have the QEMU process with the normal emulation, and then I added this LD_PCI part here, which is basically a kind of a dynamically linkable, or the patch set necessary to be able to dynamically link in different device models. So if you look at the blue device instances there, they are then instances of QEMU class objects. So I needed to be able to add types dynamically and then instantiate them. And those types, basically we have only one major implementation so far, and that's the device under test. But we wanted to be able to create a tool that would be usable for other projects as well. So then we decided that we needed to have a kind of a wire protocol to be able to communicate with these simulators that had to run in the simulation farm. Particularly this one had to run on the hardware simulation farm. And this one was, the high-level simulation was kind of complicated enough that it could be useful to run it on a separate node. So, and then we decided that we would use PCI Express transactions as the communication protocol there. And we also were able to, so we wanted to add also support for ease of debugging. So we added serial ports, multiple serial ports, and we also the firmware that runs on this card runs as a separate, can run as a separate process or linked into the simulations. So that we wanted the firmware team also to be able to use this to test early, and we achieved that. So I'll probably come back to this later, this picture. So what is this LDPCI? So it's a plugin framework, as I mentioned. It is a single API header file with minimal include dependencies. Currently it has less than 10 callbacks that is implemented by the device model. And it has some 30 utilities that is basically as much as possible now one-to-one mappings to QEMU functions. So I have this patch set now that I've been maintaining over the years, and it is, you can see the size of it there. I had to change 16 files, I added 2 files and changed 14 files, and there is, so it's a fairly small patch set that is necessary to implement this the light blue LDPCI box there that the model goes within. And the reason why I needed it to be a single API header file was because this, to be able to sell this in, I had to have it working on VirtualBox as well. And so the initial version worked on, was able to, I had a similar implementation of the framework on VirtualBox, and then the plugins could be used interchangeably on VirtualBox or QEMU. But that's not the case anymore since we kind of moved on with the QEMU implementation. But I do have benefited from this by being able to use it in a fake testing environment that I'll probably mention later if I have time for it. So the ability to have a very limited API made it useful and can make it useful later as well. So here's what it looks like when we use it. So we use command line interface to QEMU, but I have some shell script management tool on top of it that I will mention later. So what happens is that during PCI Express enumeration and the device realization in QEMU, the normal path is followed in QEMU, and then at some point it checks, it doesn't find the device model because the device doesn't exist. Then it will call this patch set that I have, and that patch set knows how to, from these command lines that can be supplied, then it knows that there is a device here that is called CIF, which is our internal name for this HCA, and it has a configuration directory in that path, and it has the ID is necessary to plug it into the PCI Express bus, and then it's going to go into, or to talk about it in hot plug and so on, and it has to go into PCIe port 0. And this then triggers a DL open so that the device model gets loaded, and you can have, in theory at least, have several .so files that add different device models. And then during instance create, this SO file gets, or the API there gets called for this particular implementation, and within that implementation we read the configuration file, and that for our device model we then try to connect to the simulator, and if that works out, then the simulator takes over and does a lot of the work, and it's the plugin is only forwarding transactions to the simulator. But I very soon figured out that it was not very useful. It was very cumbersome to work with if we were completely relying on the simulator instance to be connected, because you can imagine what happens if you have a PCI device and the device doesn't answer a CSI write, or a CSI read doesn't terminate, then the machine becomes very stuck. So we needed to have some kind of fallback implementation to be able to handle the situation where there's no simulator, or the simulator crashed, or something happened. So that means that there is some logic in this component that in the plugin that will just answer yes, 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 yes to everything that it gets presented with, so that the kind of user interface, the machine continues to work and you can do stuff with it, and later on hot plug to get device enumeration over again and get the simulator connected once it's up and running again. So similarly, on device unrealize, we do the disconnect from the simulation if necessary, and then delete the device instance, and there's a reference count on the number of devices that's using this particular model, Once it goes to 0, the type definitions are removed and DL close appears. And that's very useful because, at least during the early development, we could then have the virtual machines running. We could recompile the model and then hot plug it, and the whole device, the development cycle was very short. So, moving on to InfiniBand, I have this small example here that I used to run for my students at university that I thought might be useful to you. For some of you that are not familiar with how InfiniBand communication works in practice, because this is kind of useful to understand the challenges we have in implementing this. So typically, and then this is kind of a ping-pong example with InfiniBand, the Hello World program almost. So it's not trivial, but it's relatively simple. So we have one user process here that typically will allocate some memory. And this memory will have to be pinned to be able to the device, to be accessible for the device. So that means that we have to call this call in the user level part of the which communicates with the kernel to set up a pinned memory mapping called an MR, a memory region. And then we typically will need to create a couple of queues. We will have completion queues for completion notifications. We would have queue pairs, which are send queues, and receive queues, which are for the actual communication, for the data going by. And then similar on for the other process that we are going to communicate with. Then we need to decide, this process number 1 would need to decide where to receive his message. So he allocates some memory in this memory region and calls IB post receive to say that I have this receive buffer, make that available for communication for the InfiniBand device. And then similar on the other side, would have to make a receive buffer available, and that receive buffer could be a scatter list if necessary. So the memory can be taken from several segments to be able to use this, to do this in a efficient way without copying, because that's the primary goal of InfiniBand, is to be able to communicate 0 copy, or 1 copy is really, yeah. Okay, and then we want to send something, so then maybe this user process 1 here would have some list of items it wants to send to the other side. So that will typically then be posted as a send request. And once that's posted, the hardware will send an IB packet with that request, or end up sending IB. This is a send request then. So it will send the packet over to the other side. And on the other side, this user process 2 would poll its completion queue. It could wait for events as well, or have it interrupt driven, but this is the fast pass scenario where it's active and polling and waiting for packets to come in. And then at some point, the packet arrives and the completion is written by the hardware into the completion queue. And then the user process can then pick up the result, knowing that now the result is in the receive queue entry that it received, so it will have received the data there. And then it can we go the other way to send back again. So, yeah. And finally, there's a new completion posted. I didn't mention that there's also send completions here. So the first completion in the user process 1 there is the send completion. it can request a completion notification when the send has been performed, but that's optional. So that's how InfiniBand works. So InfiniBand works very much in that the device is taking stuff from memory, putting it directly into memory on the other node. So when we then try to look at the device and see how we should model it, it's interesting to look at how this device communicates. So obviously it has a PCI config space. It has our device has 3 bars, one firmware access bar, which is used to communicate to the firmware, and one MSIX bars for the interrupt for the MSIX interrupts, and one work request posting bar, which is used to post. It's similar to what the Mellanox calls blue flame, which is basically to write a request directly to the hardware. We call this collect buffers. And it has the MSIX support for interrupts, of course, and it does lots of DMA. And DMAs are triggered by these work requests, and it's implicitly done by the device. So initially our implementation used a lot of directly QEMU support, for instance, for MSIX handling. That were already convenient functions to handle that. But as our simulation environment matured, we moved more and more of the functionality over to the simulation side. But we still kept the logic to be able to kind of use both for the next project. So, of course, when you are a driver developer, there are some key issues. And for me, I think one of the key issues is driver development cycle time. For all developers, development cycle time is really important. And just to give you an example how our development cycle time is much better using QEMU than using hardware. You can just look at this. We have the servers. For some reason I don't understand, it seems like the more complicated the server is, the longer it takes to boot or even get out of the BIOS probing phase. So the server that I have for hardware testing, the single server I have with hardware on that I use, takes 3 minutes from I press the reset or type the reset command in the console interface until I am able to log in via SSH and start working. For the VM, that time is 30 seconds. This was actually, it's too much, but this was actually measured from my home office, so it was with some delay. So it's less than 30 seconds actually. The VM to boot takes not that much time. At least not if running, for instance, Fedora with systemd. So obviously the server side is really the BIOS probing and stuff takes a lot of time. And but by moving to the hot plug scenario, for the scenarios where that work, where the machine is not completely dead. This goes down to about 11 seconds, which is really good because, and I think if you think about development cycle time, I think it's very important to, for me, the kind of the threshold is when the time is long enough that you need to make a context switch and do something useful in between. You can have the coffee break time kind of length, where everything, at least my brain, everything is blown away. Or you could have but as long as it's within the 30-second range, it's possible to just take a sip of coffee, lean back, and be in the same context and continue to work again. While if it goes to 3 minutes, that's too much. then my thoughts at least are somewhere else, and I have to kind of, what was I doing again, kind of thinking. So I think it's really important to have that small development cycle time. Another very important thing is observability. For InfiniBand, a lot of stuff goes on in the hardware at very high speed. It's very hard to observe everything without affecting the performance or affecting the timing or the output in general. So in a simulated environment, that's much easier, of course. And of course, debugging facilities. Also, QEMU provides some interesting support there that makes debugging much easier, I think. And for test coverage, it's always the question of, once a project has arrived to a certain stage, it becomes a question of how much do you dare to change without breaking things. And in my experience, the better the tests you have, the more you dare to change, and the later in the project. And that's really good, because then you can actually do things the right way. And by having virtual machines to do some of the testing, we could do a lot more testing than we would have been able to do if we would have to have new machines or separate machines for all the tests we need to execute. So, some of the debugging. So what we added was we have added a lot of debugging features in the QEMU part of this. For instance, we do a lot of snooping so that we can actually see all the traffic coming both from the simulator to the machine and the opposite, and do that by just linking in the same libraries as we use for the driver to be able to do this at the source code level and get full overview, as opposed to when we have to do this with the hardware. The few times now that we actually have to debug things on hardware, if we are not able to reproduce it on software, we would have to use a tracer, which has a very old-fashioned interface, low-level interface. Takes a lot of time to sift through. If we are able to trigger the right scenario within the time that before the trace buffers fills up, it's really difficult to find where it is, and takes a lot of time even to set up the scenario. So we save a lot of time from being able to debug things on the software side. Also, we have it's a very heavy contended resource, a very expensive box, such PCI tracers. So not always, it's much easier for us whenever we can do it with the simulations. So we have this RTL simulation where we can actually run the exact thing that in the chip that will be in the hardware, and it's kind of painfully slow. And we were able to actually use this to success sometimes during our development. We were able to find the problem, run a test with accurate waveform output and send it to the hardware engineers, and they would spot errors in their code and fix the bugs before takeout. So we were actually having quite success with that. We should have had much more success, because we should have had this tool much earlier so that we could have detected even more bugs, but we found our share of bugs. So one of the things we early figured out we needed was a safety net. While we had this model that it wasn't, the hardware was not finished and the software wasn't finished, and you have this, the driver requests some address to be fetched from memory by the device. It's very easy to make mistakes, so that it reads from somewhere else, or even worse, write to some random location in the kernel. So the first thing we really wanted to have in place was IOMMU support, so that we could trap all the accesses to memory that wasn't really set up to be communicated with by the device. So we wanted as much control as possible there. Unfortunately, there weren't any virtual IOMMU support available in QEMU. Later we had some successful work. I got some good help from Jan Kiska and it ended up in the GSOC project, and we got IOMMU support, for Intel IOMMU support. But early on I had to kind of make a quick hack, and I successfully did that with just implementing some an extra CSR page in the device, and some callbacks in the DMA API in the kernel, so that we could have the driver actually just write, set up through all the DMA callbacks, setting up all the DMA memory, so that we could do this, have this simple IOMMU model to fault, so that actually we just disconnected the simulator each time an illegal access came in, so that we would trap the error immediately and figure out what the problem was. So that was really useful and saved us a lot of time. Another feature that was really useful was the ability to be able to do, since I'm a software guy, I really don't like having to read assembly code to figure out where the crash occurred. So I really love to have KGDB support whenever possible. So QEMU really, or QEMU, or our environment there helped a lot, because we were able to, for instance, it's very useful to have 2 console ports rather than 1, so that you get the console log or the console login in one place, and the KGDB connection in another place, trivial with QEMU. And another thing was the ability to be able to symbolically debug. It also depends on being able to load the linker locations of the modules that we need to debug into our remote debugger through the console. I was very pleased with this simple solution, where we have a script we use to load the driver when we load the driver in the environment, in the test environment, and the driver will then, and that script will also record in an NFS location where all the symbol information for where that driver ended up in the kernel, and that will then be available also after the machine has crashed. So that we could actually, so now routinely, if I make a mistake and have a null pointer exception, I can access the console and get full GDB symbolic output, and much faster figure out what went wrong. And I can even do that with 0 devices. So one thing I can't do on hardware is if the driver faults already during driver load, that's before the symbol information is available and written. I couldn't do that on hardware because I can't hot plug this device that is physically in the machine. I can do that on QEMU because we have QEMU hot plug support, and then I can just start with 0 devices, load the driver, plug in the device, and it will fail and fault, but then I have the symbol information. So this was really helpful. The problem, of course, with this is this nice figure here. You can imagine these tools. I think I have like 7 different tools that I'm maintaining, more or less. And my main goal was to write this driver. We have a team working on the driver, but still a lot of time goes into these tools, unfortunately. And not only did we have to do the tools to have tools to do this, to have the plugin and everything, but we also needed to manage hundreds of VMs. And we had this very shortage of disk space early on that I told you about. So I had to come up with just a quick and dirty solution to just not have to tell people what command lines to use with QEMU. So that resulted in what is this shell script thing that I maintain, that is kind of a virtual machine memory management system. Yeah. So that script soon started to become a lot of stuff. We had a lot of features we needed, as you can see. PCI or PCI Express, boot number of root ports to use, VLAN support, multiple subnets, bridges, disk interfaces, Ethernet model. Lots of this were required over time. I even used it with the pass-through because we wanted to support our SRIOV support and the DFIO. Yeah. So our deployment today is we have this continuous integration based on Jenkins and Gerrit. Every commit we submit goes through a two-stage test. There is a smoke test that runs in parallel very quickly to kind of filter out the obvious mistakes, compiling and stuff like that, and some smoke tests. Actually based on G-test, most of it. And then we have a longer serialized, it has to be serialized because of the amount of hardware we have available. And check-in regression tests that actually will result in commits being accepted. And we run a lot of test applications, both our own in-house developed unit tests based on G-test, and simple system tests, and a lot of other tests. We have several tests systems that we have developed to have more tests. We couldn't have achieved this without virtualization because we simply don't have enough hardware to do it. So what did we achieve with this? Well, we had the ability to start very early in the development. We found a lot of bugs, both before and after tape-out. We found both hardware and lots of software bugs, of course. I think we had a significantly shorter development cycle, both for the firmware and the software, the driver software, and user-level library. And we actually had a working driver on the day we got the first hardware in the lab. And in the longer term, we expect to benefit more from this infrastructure that we built up by being able to leverage on future projects and get even further now that we don't have to make all the tooling in the first place. And the question is, what more could we have done? And I think we could have done a lot. I'm really excited about it. I think we could have done, the sky is the limit. We could have we could have more simulation environments, but it's really a resource allocation issue, I mean manpower issue, and it's also to a great extent a trust issue. If you're trying to do something like this, you would need to have some trust from management, because I've seen projects where people try to create a lot of fancy environmental tests and lots of simulation models, stuff like that, and the models ends up not being used, and a lot of time has been wasted. So management is typically very, and has to be kind of critical to a lot of upfront investment in test environments, because it can go wrong. So it's a matter of trust in that sense, and competence, of course. Some of the challenges we have, of course there was a lot, I had to rebase a lot of times, but that's our own fault since we couldn't open source it at that point. Hopefully we can now. But that's also for the good, of course, because a lot of this patch set has actually shrunk over time. It was more complicated in the early versions. Now it's much more elegant and shorter than it used to be because of the developments in QEMU. One other problem I had was that PCI Express has a memory consistency model where writes are ordered. That doesn't really apply in the QEMU sense. When you have DMAs coming in, you don't really have an ordering of memory. So I had to actually, some places I had to insert knowledge about required ordering by having introducing memory barriers. Some places in this device emulation model, just to be able to get the model that we rely on in our hardware or in our device. Another challenge, of course, was to kind of, as this took off and people started to using it, the other slide told you what that was all about, and the maintenance of VMs. And I wanted to do, several times I looked briefly at trying to go to use Virtual Manager, Overt, all the new stuff to do virtual machine management, but there simply wasn't enough time to get rid of the shell scripts. Another very interesting problem I have that is obvious when you start to run with a slow simulation model is that there is a timeout. We have this, what I call this timeout scaling problem. If on hardware, something that takes nanoseconds can take tens of seconds on the RTL simulation. What is nice about it is that I can actually see the package pass in real time. So I can have a cup of coffee and watch and see, oh, DMA read, DMA write, work request, everything in order, in a kind of slow pace suitable for my brain. But the problem is that the kernel becomes really angry if it has to wait for 25 seconds for something. You get into kernel soft lockups and even hard lockups. That was kind of problematic to handle. What I did to alleviate the most serious problems was to add some patches to some of the modules in the kernel to avoid it from timing out by having this scaling, timeout scaling factor that I kind of introduced and were able to set differently for the different simulation environments. But that's not good enough. I haven't been able to handle the network stack, network timeouts. So when we tried to run IP over IB on this hardware, slow hardware simulation, we ran into problems because Ethernet would time out, IP would time out, TCP would time out long before we got to actually serve. So that's something I wonder. That's something to work on. This is to how can QEMU help in that sense. And for the QEMU related work is this some of the getting the patches that I have in the queue were merged. Better tools. One thing I'm intrigued about that I'd like to see if there's a possibility to be able to actually halt a virtual machine in the kernel from within the virtual machine, from beneath the virtual machine. Now I'm able to recompile with KGDB breakpoint and then hot plug, but I would like to do even better than that if I have a machine that is stuck. Yeah, I'm running out of time, I see. So a lot of this has been also about changing people's minds. So lots of social engineering, try to kind of sneak things out, try to convince people that it's in their own good to work test-driven, that we spend time on tooling. Obviously, their evolutionary approach. One thing I'm kind of fond of is to think of that developers also need things to be neat. So all the test environment for people to start using it, it should look good. You should get a good feeling if the tests pass, and a bad feeling if they fail, so that you are inclined to fix them. And finally, my personal takeaway. If you want to understand how a particular piece of hardware works, try to write an emulation for it. Questions?
Hello. You mentioned using KGDB for debugging your kernel. Is there any particular reason why you didn't just use QEMU's GDB server?
To use?
QEMU's GDB server to debug the kernel.
I think I wasn't aware of it, or not aware of it. Obviously, I should look into that.
Yeah.
So you mentioned you are doing this as a SRV device, right?
Yes.
So do you actually test like multiple virtual functions?
Yes, I'm able to use SRLV and instantiate virtual functions, and that's why the SO file is able to have or needs to have more than one device model, because it requires both the physical device model and the virtual device model to kind of.
Okay, but do you rely on you mentioned this virtual IOMU patch, right? Do you rely on the virtual IOMU patches to rotate the multiple request ID for the DMA?
No, that's something the SRLV patch will take care of.
Oh, okay.
Yeah.
Okay, great, thank you.
Hello. You mentioned that the RCH device has a MMU unit, right?
Yes.
So my question is how to emulate this MMU unit into QEMU?
Oh, this particular MMU test facility that I was talking about was just an extension to the device model, a simple extension that just checks all the addresses, creates a table of all the addresses that it receives via the DMA API. Because there are a set of I mentioned the DMA API. There's a DMA API in the driver where you get callbacks, where a driver can get callbacks for all types of DMA accesses or set up DMA mappings and unmappings. And we just implement those callbacks for the purpose of testing, and then writes to a special CSR page in the device where the QEMU side picks that up, and the model picks that up and adds to that table. So it's kind of a fake, simple, poor man's IOMMU solution.
Okay.
That answers.
So what will happen if the guest changes the page table for the virtual device? I mean, if the VM change the MMU for the virtualized device, how to handle it?
Well, are you talking about MMU, IOMMU
No.
changes?
The MMU on the RCH device, on the virtual RCH device is a VM.
Yeah, so this works the same way as it's kind of the way the RDMA stack works. You map memory to you pin the kernel will pin the memory that is accessible, so that memory is locked for the entire lifetime of that region, and then it gets unmapped, and then the device will destroy the binding. So the binding will always be static, kind of for the lifetime of that binding, while for the device seen from the device. So there's no we don't have in this device. There's no support for page request interfaces. If that's what you're talking about, kind of dynamic paging and stuff like that from the device.
Okay, thank you.
Other questions? I'm almost running out of time. So. Okay. Thank you.